Hello, good morning. We have a midterm exam 1 week from today, and there's a homework due on Wednesday, which is also officially on D12. It says March 2, Wednesday, but it is okay. Oh, Friday, that's also fine. The midterm exam is on Friday. And as usual, look for basically base it around homework. And when you struggle with homework, go into lectures and then going to textbook. So it's sort of a circle. It's primarily around example problems, which again, there could be many, but go for the ones of the kind in the homework. So that's an advice to study. The old exams should be a resource for the kind of questions I do ask. The only change might be that more recently, in the last 2 years, since pandemic started, that's what made me do that. I've been asking conceptual questions, which is to say short answers, which sometimes comes out high, but at the same time, I do ask about maybe about 25% of the questions are concept based. Any questions or comments? We still have the attendance low, but that I don't know how to gauge that, but we'll proceed as is. We have only about half of the students showing up in the class, but that also might be an indication I have really not matched up with the names of students who come in the class as to in the grades also there is a clear disparity. So it could be that, but it need not be that either. So we don't have to make conclusions, but yeah, hopefully lectures help. If you can manage, that's perfectly fine. Okay, we were discussing the idea of magnetic force. We introduced the idea of electric force earlier. The main thing we have done is that if there is, whenever there is an electric charge, I can write things down. You have electric force, electrostatics, we call it. You have the idea of electric charge. Experiences an electric force, or there is an electric force between two electric charges, the idea of electric force. And we introduce the idea of electric field to understand electric force, and there is the electric energy. And a significant application of this are electric circuits, which has pretty much changed our life, especially if you imagine in the last 200 years, there has been a significant development as due to our understanding of electric energy. Electric force leads to the idea of electric field. And electric energy leads to the idea of electric potential. That's the very, as far as keywords go in the idea of electrostatics. Here, what we are talking about now, we are doing magnetostatics. Basically, the idea of magnetic force, it centers around the idea of magnetic force. And here, the idea is it's the same electric charge, but it is moving electric charge. It's not charge we are interested in. Only when the charge is moving do they participate in the magnetic force. By a moving electric charge, we will also mean the electric current. A current, when we say there is 3 amps of current in a wire, they are basically due to the motion of charges. That's the same idea. In fact, we will very quickly in the next lecture switch over to the idea of currents. That will be the basic way we will, that's one way of looking at magnetostatics. Moving electric charge, here we use the symbol Q to represent charge. Moving electric charge would be Q times the velocity. So what is the source of an electric field or an electric force? It is a charge, and often we describe this as a positive charge corresponding to electric field coming out of it, and there is another positive charge in here which experiences a force, and that can be thought of as the electric field coming and ending onto, I should say negative charge. That positive charge will not. So this should be a negative charge if the lines have to come and stop at that point, and that experiences a force. We want to have a similar interpretation here, but now in terms of magnetic field and magnetic charge. So instead of talking about what is the magnetic field created by this, we have been talking about what is the magnetic force. First, let's understand what's the magnetic force, and we would of course like to talk about magnetic energy also. We won't be able to go too much in detail about what kind of magnetic energy is stored. Magnetic energy is typically stored in coils. So anything when you have a charge, when you have a current passing through a coil, that's what stores magnetic energy. We will not be doing too much of that, but we will introduce the concept. Here, let's talk about what is a magnetic force. And I again forgot to move this. So magnetic force here has the expression, we introduced it as F is equal to, as far as notation and writing goes, since it's a vector, it's written as a cross product. That's QV, and this is a mathematical operation, meaning it's a vector product. So that's a symbolic representation of the magnetic force. But the main idea is what is the magnitude of the, whenever you have a vector, what is the magnitude of the magnetic force and what is the direction of the magnetic force. Magnitude is given by the magnitude of the force is the charge itself times the magnitude of the velocity, magnitude of the magnetic field, and this cross product contributes to the angle between the velocity and magnetic field. So this is the angle between the velocity and the magnetic field. So a picture would be, that's your velocity, that's your magnetic field, and that's the angle between them. And that leads to the idea that if velocity was in the direction of the magnetic field, then the angle theta here, so if the velocity was in the direction of the magnetic field, angle theta is 0. And if theta is 0, sine of the angle is 0. Sine of 0 is 0. That means to say there is no magnetic force when a charge is moving in the direction of the magnetic field, which is counterintuitive when you think about a cause and effect. If I were to push something, it is expected that it will move in that direction. But that's not the case in the case of magnetic field. If you want to use the idea of magnetic field for maximum effect, you want to go perpendicular to that. It is like bicycling, if that is a very similar idea, and that is because mathematically this cross product has this non-trivial feature that when you're bicycling, when you're falling to the right, you turn your handle to the left, right? That's a basic idea. It is usually you would think that it should be in the same direction, and there it is a different concept altogether, but it's the same cross product. Mathematically, it's the same cross product that comes in, and that leads to the same idea there. Magnitude again, SQV again. One more point is that if velocity was zero, if something is at rest and if you try to push something, you expect it to move, but no, if it is at rest, it won't have any effect on it. So it has to begin moving for it to start showing the effect. Direction, we said, is given by the right-hand rule. We used the right-hand rule. In one way, I described it. There are many ways of remembering the right-hand rule. You can use whichever way you want to, but that one I have suggested in your textbook. There are a couple of methods to remember that. Either way should be good. Let's here talk about given a magnetic field. What happens to it? We already said that it will start moving in circles. The basic idea in a magnetic field is that any charge, positive or negative, it starts moving in circles. And the moment it starts moving in circles, the question you can ask is, what is the radius of the circle and how often does it move around it? What's the frequency with which it goes around it? So let's do that for a charge. So circular motion in a magnetic field. So let's say we should move this. Let's say that is a magnetic field given. It's convenient to make it go into the boat so that the motion itself is happening on the plane of the boat. Remember that because of this vector product, only when it is perpendicular to it, you get the maximum effect. So, that's your magnetic field that is going into the boat. That's your speed. Let's say it is 0 point. So it is. I should also maybe say that's your x, y, and z is coming out of the boat. It is good to emphasize at this point, maybe it is not, you might not have noticed this. Whenever we have a coordinate system, we first say x and y. Once you choose x, it is commonly you choose the other axis as y. Right? So that's your x and that's your y. That seems to be natural to do. But from that point on, you can ask, what is the direction of z-axis? Is it coming out of the boat? Is it going into the boat? Or does it not matter at all? And it might seem that it should not matter at all. And of course, at some level, you can say it should not matter. Physics should not depend on what kind of choice you make. Like nature should not care for what you do. But for sticking to the notations that are already existing for things to be compatible, it is necessary that once you have x and y, z has to be coming out of the board. In what sense? If you do x crossed with y, x hat crossed with y hat. By that, I mean the same, use the right-hand rule to get this. Whenever I say cross, you have to use this idea of right-hand rule. Like point the fingers in the first vector, so that's x. Point your palm in the second vector, so that's pointing up now. And then you open the thumb, and thumb is coming out of the board. So that's necessary that z has to come out of this board. So x crossed with y is equal to z hat. If you choose it to be into the board, that's called a left-handed system. And for consistency with let's say other work around, we have to use the same notation. In principle, at some level, you can say it should not depend on the choice that you're making. But if you want to compare things, if you do some work and you want to talk to another experimentalist or another person who has done a work in another country independently in his own coordinate system, then you want to make sure that what kind of coordinate system is being used, and this is called a right-handed coordinate system. In that coordinate system, let's say the magnetic field is in the, now it's going in, so it is minus v hat, and let's say it is about 0.02. We said 10 raised to minus 4 Tesla is the amount of magnetic field present on the surface of Earth, which is created by Earth itself, and the unit of magnetic field is Tesla, right? T. So that's the magnetic field, and let's say that is a, let's do two things. We have a positive charge that could be a proton, so that's a proton, so positive charge proton. Proton has this feature that its electric charge is 1.6 into 10 raised to minus 19 coulombs. That's positively charged. And its mass is 6.7 into 10 raised to minus 27 kg. That's really tiny, but then it is one of the building blocks of matter around us, and we can ask what is the what kind of motion does it do? It is a positive charge, so it will take a, it will go in a circle, but then what's the radius of the circle? What's the frequency with which it goes? We would like to compare this with, let's say this is the charge of the proton, as the charge of the electron is the same, except that it is negative, right? So it's minus QE. But the mass of the electron is significantly lower. It's about 2,000 times smaller than the proton. So this is equal to 9.1 exact number. That's about 10 raised to minus 31 kg. Notice that it's a bigger number, but it's a bigger negative number. So it is significantly smaller. And this is about, so you can say mass of proton is approximately 1,800 times the mass of the electron. Like to 2 sig digits. So since we are working in 2 sig digits, that's equal to 2 significant digits. That's exactly correct. So in that sense, now let's ask, okay, if you are given the velocity of this charge, what happens to it? So let's say it is moving with a velocity v. At this point, let's not specify the velocity. We will come back and specify the velocity. Let's show that certain things are independent of the velocity itself. If it is a velocity v, and very soon at the bottom I will do for a negative charge also. If we have a velocity v, first we have to find the force, direction of the force. We use the right hand rule, point it in the direction of velocity, palm in the direction of magnetic field. It is pointing into the board, and open the hub. So that's your force. Right, that's the direction of the force, which means that it will pull it that way, but we also know that it is going to go in circles, so this will start going in circles. And our immediate goal is to find what is the cyclotron frequency, and that's given by Q times B over M. That was an immediate conclusion we made by equating force and the centripetal acceleration. That's an immediate conclusion that comes out. And notice how it does not depend on the velocity. It does not matter how fast you're going once it goes in a circle, how many times it will go around the circle. This is the angular frequency, how many revolutions it makes around while going in that circle. That's what it is. And this is equal to, let's put in the numbers. That's 1.6 into 10 raised to minus 19 times 0.02 and divided by the mass, which is 9.1 into 10 raised to minus 31. And that comes out 2. So that is, let me do this for completeness. And that's 1.8. So that is minus 12 coming from here, minus 19 and minus 31. Sorry, plus 12. That loses 2 there. That's 10 raised to 10. That's about 1.8 into 10 raised to 9. This is radians per second, so it is radians per second. So that's, notice this number is really that how many times it goes. This is angular frequency. In principle, the frequency itself, how many times it will go. You have to divide it further by 2 pi, but that's a factor of 6. So it's of the order of 10 raised to 9 times. So that's really fast. That's the number of times an electron, if it sees a magnetic field, that means to say, in this room at this point, that is a magnetic field of about 1 Gauss, which is 10 raised to minus 4 Tesla. If there is an electron around here, and if it is moving, irrespective of what velocity is going with, it will start circling that magnetic field, whatever the direction it is. It will start circling with around that, and it's extremely fast. It goes about 1 billion times per second. So that's a very fastly circulating effect, but that's what an electron does in a charge, and it always does that. Let's do the same thing for an, I talked about a proton, but then I worked with an electron. So this is for an electron. The calculation is for an electron, but the diagram I have shown is for a proton. So what changes in the for an electron? It's one very straightforward thing, that it's a negatively charged particle. And so it is, so this is a negatively charged particle. Let's say it's moving with the same velocity v. But now, how do you calculate the direction of the force? You do the same right-hand rule. It's pointing in the direction of v, magnetic field going in. You open the thumb, it is going to experience a force F, but that's for a positive charge. Whatever result you get, you flip it. So that's the direction of the force it experiences. So this is for an electron. The diagram is for an electron, and this is for a proton. A positively charged particle. And the calculation for a proton I'll do in a minute. Yes.
So the calculation you just did is actually for the electron.
That's correct. Yeah, that's what I confused. Sorry about the confusion. So this calculation is down here. Right, and I'll do the calculation for the proton in a second after this. Okay, my bad. Any other questions on that? So the calculation for the electron, the diagram came after the calculation. This will also go in circles. This will go in a circle here like this. Right. So, and again, you ask how many times does it go? That's the number of times it will go around in a circle, angular frequency. What changes for a proton? So now let's say what happens in a proton. So the calculation is pretty much the same. So let's call it omega p. This is equal to q times b over m. So this time you replace the charge of a proton, but charge of a proton is exactly the same as a charge of an electron. So the numerator remains the same. The magnetic field is the same. And the mass now, this is a proton, it's significantly heavier. So the number will be smaller. So it's about 2,000 times heavier. That's 6.7 into 10 raised to minus 27. And that is equal to so this time is 7 plus 1, 8. You lose 1 there, that makes it a 6. So that's 4.5 into 10 raised to 5 radians per second. Notice this is of the order. If you divide the two, they should come out in the order of about 2000, right? 1800, we said mass of proton and mass of electron is 2000 times of each other. And the and the frequency should reciprocate. Okay, that's the cyclotron frequency. That's how many times it goes around in a magnetic field. But then you ask, what's the radius of this? Like, so all the electrons that's in this room, they're actually going around in circles while they are tracing the magnetic field. So what is the radius of this circle? That's another thing you could ask. And that's given by whenever something is going in a circle, you say it's 2 pi r over time period, and that can be converted into velocity over the angular frequency. Right? So if you think of this, this is 2 pi times r, and there is a 1 over time period in it in the frequency. So that's how velocity is related to the radius. So this is given by, now we need the velocity, how fast something is moving, that matters. So what is the typical velocity of an electron? We can think about, last time we talked about northern lights, and in northern lights, when the particles are coming from the sun, they are very high, very fast moving particles, and they could be very close to the speed of light. But let's make it slightly slower. Let's say 10 raised to 5. So let's say V, velocity of both these protons and the electron, is about 1.0 into 10 raised to 5 meters per second. That's an additional information we give that depends on the system we are talking about. If we're talking about northern lights, they're moving significantly fast. But when things are going inside an atom or inside an atom also, it goes fast. In your lab, it need not be going that fast. That's the point. So here it is 1.0 into 10 raised to 5. This is now the radius of the electron. Right? So then you say velocity, we keep the same. And that's the rate angular frequency of the electron. So that's 10 raised to 5 meters per second divided by the angular frequency. That's 1.8 into 10 raised to 9. So that's 10 raised to minus 4, and that's 5.6 into 10 raised to, so that is a minus 4 and one more for the number I have. So that's 10 raised to minus 5 meters. That's really small. 10 raised to minus 3 is a millimeter. A millimeter is the smallest division that you see on a handheld ruler that you carry in your carry with you sometimes in a box. So that's 10 raised to minus 3 is that much. So break that into 100 times, and that's the radius we are talking. So it's really tiny radius. So this is almost a micrometer. What about the proton? Does that also go that small? Probably not, because that's a significantly smaller number. So let's say this is radius of a proton in the same, when it is moving with 10 raised to 5 meters per second, we have divided by the frequency, which is 4.5 into 10 raised to 5. Already the 10 raised to 5 cancels out, and it's about 1 over 5, so that's about 0.2. So that's about 0.22 meters. It is 22 centimeters, and that's about this, like that's about your arm length, and that's the radius of the proton. So if in this room we have a magnetic field of 2 Tesla, 0.02 Tesla, and an electron and a proton are moving in it, an electron will go really tiny micrometer radius circles and very fast, and a proton actually will have 22 centimeters. So it will go in this big circles while going around the magnetic field about 10 raised to 5 meters per second. So that gives us an idea of what a charge does in a magnetic field. Now, the immediate thing is what we can do with it. So now we have an electric force and a magnetic force that can control a charge. And the immediate idea is that what if we put both together? And one immediate application of this is what is called a velocity selector. So the application is called velocity selector. Again, remember that now we are working with charges. One of the motivations or one of the, if you want to really work with charges, you should be able to control them. And by controlling, we mean we would like to select the charges that are moving with a certain speed. Like if you're doing mechanical experiments in your lab, then you can manage it, how much you push on some material that decides how much speed it will gain. But if you're working with charges which are really small, electrons and protons, how do you control its velocity? And this gives you an idea of how one can control it. So let's say you have a region of magnetic field. First, let's have an electric field going in this direction. That's electric field. And the magnetic field is going into the page. So the lines are electric field here, and cross is the magnetic field. Magnetic field is going into the page, and electric field is going to the right of the page. If there is a positive charge here, it will experience both electric force and magnetic force. Electric force will be to the right, whether it is moving or not, it doesn't matter. It will experience a force to the right. And now we have a magnetic field also, and we have to talk about what is the force it will experience. It will, if it was, we will make it move in this positive direction. Let's say it will, positive charge moving in this direction, and we would like to know how much does it move and in what direction does it move. But the basic idea for that will be, so let's say how do you generate this beam of charges, right? So that's so to give the motivation for the velocity selector. So let's say let's ask the question of how are charges made to move? Like we don't have too much control on it, they're so tiny, but when they are taken as a bunch, we have some control on it. So what you do is you take basically a small box of 1 centimeter by 1 centimeter by 1 centimeter. So let's say this is for 5 centimeter sized metallic object, and you heat it up. So you heat up this significantly. If you raise the temperature, if this is gas, all the gas starts moving around. So they start moving around in all directions, and more you heat up, more it's moving. So, but they're all moving randomly in random direction with their own speed that they have. They're going significantly fast, but still each one is going with their own speed. So you heat it more and more, they're going faster and faster. And while they're very hot, you make a small hole. And you make a small hole in the container, and some of these charges, whichever is going in that direction, starts coming out, and suddenly you have a spray of charges if you want, but they're all going in different directions with different velocity. So at least let's control the direction first. How do you control the direction? You already made a hole, so you make another metallic piece which has a hole in it. So many of them get obstructed, and only the ones that are actually going in straight line will actually come out. Only they survive. Put in one more hole if you're really picky, if you want to be very careful. And by the time you have put about 2 or 3 holes like this, only those charges that are actually going vertically outward or vertically straight upward are coming out. So they all have a velocity v, but not the same velocity. They are all moving in that direction, but they need not be going with the same speed. One might be slower, one might be faster. Only thing we can be sure about is that they are all moving in that direction. So this is called a collimator, just for completeness, I'm pointing that out. And now the goal is you have this velocity, a set of charges that could be millions of, usually very large, 10 raised to 20 number of charges. They are all moving in a straight line, but they have different velocities. And your goal is to select only those charges. You want to make a filter if you want, which selects only the charges that are moving with a certain very specific velocity. And that's the velocity selector. You create an electric field and a magnetic field, and whatever comes out here after passing through this is supposed to have a very specific velocity. So let's see what happens. So this charge comes in here, and that's the same charge we are showing. Let us say it is positively charged. It could be negatively charged also. Since it has a charge, it experiences an electric force. There is an electric field. It experiences an electric force. So that's your electric force Fe. That's to the right side because the electric field is to the right hand side. Positive charge, it experiences a force, and that's equal to Q, whatever is the charge, times the electric field. And electric field we know how to create, which just use 2 metallic plates like a capacitor is used to do that. A magnetic field, you'll create it using a magnet. What is the force it experiences? You use the right hand rule. The positive charge is moving upwards now in the upward direction. That's your 4 fingers. You point the palm in the direction of the magnetic field. That's the magnetic field. And you open your thumb, and when you're pointing in this way, it is actually pointing to your left. And that's your magnetic force. That's your magnetic force. And the magnitude of that, so let me write it. So this is equal to Q V cross P. We will be interested in the magnitude. So the idea is electric field pulls it to the right, magnetic force pulls it to the left. One of them will be larger in quantity, whichever is stronger, it will move to that direction. But there is a balancing act. If these 2 forces were exactly the same, then it will not get deviated either to the right or to the left, and that's what we are interested in. So let's ask the question, when will, for what situation will the force of the magnetic field exactly equal the force due to the electric field? That's the idea of a filter we are making, in the idea that if this is not deviated, so if the electric force is larger, this will get deviated to the right. If the magnetic force is larger, it will deviate to the left, but there is a very special situation where this will go all the way through. And if we wait there, it will be only those charges which does not experience a total electric force that will come out. And that's what we are interested in. And that's the condition for a velocity selector, that you set your magnetic field and electric field in such a way that they cancel each other. And what is the electric magnitude of the electric force? That's Q times E. Right? By that I mean all the positive and negative signs have been taken care of. What is the magnetic force? It is Q times V times B. And there is also the sign of the angle between them. Velocity is in the plane of the board. Magnetic field is going in. The angle between them is 90 degrees. So sine of 90 is 1. So that's sine of 90. That doesn't play an important rho, that's equal to 1. Notice the charge cancels out. That's important because when you get have a lot of ions coming out of a heat bath of this kind, you cannot be sure with if every particle that is moving has the same amount of charge or not. Some might be positively charged by a singly charged ion, or that might be doubly charged ion. So we don't know. Either way, it doesn't matter because Q cancels out, and then what we have is velocity V is exactly equal to the electric field over the magnetic field. So just by controlling the magnitude of the electric and the magnitude of the electric field and the magnitude of the magnetic field, you know exactly what is the velocity that is going to come undeviated. Others will all get either pushed to the right or to the left, and you should be able to analyze under what situations will things move to the right, or under what situations will things move to the left. This is the velocity selector, so this is the selected velocity. And you can say it is clear that if the electric field was larger than the electric force, I should say, if the electric force is larger than the magnetic field, it moves to the right. It gets deflected to the right. And if the electric force due to the electric field is smaller than the magnetic field, it gets deflected to the left. And you have homework problems where you have to discuss that exactly what kind of things that go to the right and to the left. So that's your velocity selector. Once you have a beam, this is usually called a beam. Like this is a beam here, beam of charges. Once you have a beam, and now you have the additional feature that you can actually select the velocity of the beam. This has another application, and that is called the mass spectrometer. Mass spectrometer is requires a velocity selector to it, but as far as concept goes, it is independent of that. So let's so this is called a mass spectrometer. Idea is again the same. Electrons and protons and generally the charged particles are really tiny, and you would like to say, I want to measure the mass of these particles. And how do you go about doing that? For example, when you have atoms, how do you weigh the atoms, especially when they are in the gas form? You want to really pick one of them and get the mass out. So how do you do such an experiment? You use the magnetic field, and the idea is that you put them in a magnetic field. And let's say this is a barrier here, and you make a beam out of, like we already now know how to make a beam out of it. In fact, we know ones that go with a specific velocity. So this is a beam of charged particles. So this is a beam, and that's going with a velocity. So this is beam with velocity v. Usually when you discuss a mass spectrometer, you don't typically have a beam with a special velocity. Instead, what you control is the energy you provide to the spectrometer itself. Here we are saying we have jumped one step. That is basically the idea of the velocity selector, and we are directly here where we have the velocity of this charged particle. So there is a particle, charged particle Q, moving with a velocity v, And that's the idea of a magnetic force, right? Let's say it is a positively charged particle. So that's your positively charged particle, and it's going with velocity v. So that's your v. It experiences a magnetic force. We already discussed that it's in the same direction. V pointing upward, magnetic field. The palm facing the magnetic field, open the thumb, so it experiences a force to the left. And so it experiences a circular motion inside the magnetic field. And the idea now is that to measure this radius of this circular path, you make bins actually. So you make a small sensor here, you make a small sensor here, you make a small sensor here, and based on what's the charge and the mass, it also has a mass, right? Based on what the mass of these charges are, they will be collected in different bins. And in which bin it is collected decides what the mass is. So let's look at this more carefully. So the force it experiences is equal to mass times acceleration, which is, let me write it as mass times acceleration. This is mass times v square over r. And the magnetic force is Q times V times B times sine of the angle, which is 90 degrees. That's 1. Velocity cancels out. So V is known, so you have R is equal to M over, so M over Q times B. M times B, right? M times V over Q times B. We had this relation in the last class also, but now if we have the velocity selected, only if the velocity is selected, usually unless you use that configuration, your velocity is not selected. Only if the velocity is selected is this relation so simple. If the velocity is not selected, you have to do some more or some more in between in this region. But we are presuming that velocity is selected, then which radius you get the particle in decides your mass. So if you're interested in solving for the mass, you simply say it is Q B R over V. So if you know these quantities, then you know the mass. The basic thing you're measuring is your R. So you measure this, measure in the sense you sense, you put these bins here, you decide on which bin is the particle coming in. That tells you what is the mass of the particle. So a very simple setup, but it is a very powerful setup. You will see this in almost every lab that you work on these days, whether it is a biology lab, chemistry lab, physics lab. Most of the labs depends on what is the mass of the atoms that you're dealing with. And this is a very simple way of measuring the mass. Let me stop at this stage, and we'll come back and work on how currents experience magnetic forces. Thank you.
Professor, is that?
Yes.
I have a school athletic activity next Friday that I'll be gone for. Is there a time that we can schedule for me to take the lecture?
Yes, you can support. Yes, if this is a university health event, you have to provide me with a document.
Okay.
That says something that says that you're really gone. Now, what happens is that when I make a makeup test, it is not the same as the usual test. So the format might be completely off. I don't spend so much time. It can happen that it is significantly easier, but often it is significantly harder.
Okay.
Now, what I do is that I do the grading independently, and I take care of these things in the grading. And I also look at the overall performance in the semester, how sincere the student is, what's their grading, and so on. So all that is for your information. Yes, it is possible to do it, but usually I discourage students to do it because of these features. The predictability is less, but if it is important, you should do it.
I'll have the documents and the itinerary stuff, and I'll email that to you.
Yeah, just coordinate a date and time between us. It doesn't matter if it is after or before. I don't really mind.
Okay.
It doesn't matter 1 week extra or not. But if it is possible, do it before. That's perfectly fine. Finish it off. That's what I usually
Yeah,
do.
before spring break.
Yeah, so get it done with, but you have to coordinate with me. Please give me 24 hours so that I have an exam prepared.
Awesome.
For me. Okay, that can be done on email.
Yes.
And the document is important, if it has to work out.
Thank you.
Good.